Good afternoon, folks. Lately, I've been working on a toolkit to store battery testing and use data efficiently so that we can use it with artificial intelligence algorithms. And while working on that, I had to learn a lot about storing data efficiently in files. And not just any kind of data, but large tabular data, like the kind you might be familiar with if you use Pandas Dataframes in Python. Now, I'm not going to talk you through the actual code for that library. It's got a lot of extra stuff that I think would only kind of confuse the underlying principles that are going to be the same throughout many different applications. So what we're going to talk through today is how to take Pandas data frames and store them in the so-called HDF5 format. So I'm not going to actually talk about what that format is yet. But I'm going to start by saying that there are many ways, of course, to store tabular data in a file such that it can be read by either another Python program or another tool like Excel, and HDF5 is one of these. Pandas lets you write HDF5 files very quickly, but it doesn't give you much control, or at least not direct control, over how that data is written. So what we're going to show you today is what the data looks like when you write an HDF5 file with Pandas, and then how you can take the same Python toolkit that Pandas uses to write these files and use it to write the files directly, which can give you a little bit more simplicity in how that data actually looks on disk. So with that said, we'll get started with just a simple data frame. And so here I've created a data frame with three different kinds of data, an integer, some floating point values, and a list of characters. So let me clear the notebook and let's start again. So here I've got my data, and with Pandas I can save it just like any other format to a file on disk that happens to be an HDF5. Now I'm going to explain what the HDF5 file is in detail later, but let's take a look at what its structure is to get an idea about what you're looking at. So with Pandas, it stores a vociferous amount of information. We've got what version of PyTables was used to store it. We've got some detailed information about the shape of the Python data frame, a lot of additional features that are added on top, and eventually down at the very bottom, your actual data. So this isn't what the file actually looks like on disk. It's a representation of what that information contains and a nice summary made by this H5LS tool because the actual data is binary. So with that said, let's get into how these files are structured on a deeper level so that you can be able to write them your own. So the first step to do that is to understand a little bit more about what you're working with. So I've used the acronym HDF5 a bunch, and what that stands for is Hierarchical Data Format version 5. So hierarchical data format is kind of like an Excel spreadsheet. Each spreadsheet contains multiple sheets, each with their own data. So you can store different types of data all in the same file. However, unlike Excel, it is a nested hierarchical structure. So you can have sheets that themselves have sheets that have sheets, and so on. It's also, HDF5 files are also well designed for tabular data, like a CSV file. But instead of being written in a plain text format that can be read by humans, it's read in binary, written in binary, which has some advantages in that the data is stored exactly in the format that it will be actually in your computer memory, which provides a lot of efficiency and ensures you don't lose accuracy of any numbers, particularly going between a shortened version that humans can see and also in decimal, which humans can read, and a full form version in base 2 written in binary. Additionally, I like HDF5 files and use them for this battery project because they've got a couple other great features on top. HDF5 files, as we'll show later, can have built-in compression such that it's also in a way that's invisible to whoever's using that file. If I write data with compression, someone who uses that compressed data may not even notice it as they read the data, as they read it in later. Additionally, it's got some caching operations such that if I have a very big dataset file, it loads only small chunks into memory at each time. So I can manipulate very large data this way. And it's got some caching tricks that make writes, reads, and edits very efficient. Say it'll allow you to edit multiple rows, but then write it to disk only once. You create one of these files, and just like you would a normal Python file, there's PyTables.open file, name of the file, write mode. But unlike a normal Python file that you would print to or read from, it provides operations that look a little bit like a dictionary. So here I'm creating a key in the dictionary. Just like I said, these are big nested structures like a Python dictionary or a JSON file if you're familiar. And what I'm starting off with is creating a group that's going to hold on to the data table that I'm about to create. Before I can create that table, my first step is to define what are the columns in that data, what are their names, what are their types. To do that from starting with Pandas as a point, what I first do is call Pandas's dtypes.toDict operation to create a dictionary, defining a mapping between the name of the column and its data type as a NumPy type description. So here you can see we have an integer with 8 bytes, a 8-byte float, a double precision float, and an object. Now, these two are great. Almost every program language has multiple types of integers and floats, and these happen to be ones that are supported by HDF. Object is a problem. Object is something specific to Python, so I need to convert it to something more universal before I can save it to disk effectively. Now, I happen to know that these are all single character strings, so my data type for that is 1s. 1s is the NumPy style string description. If you go to this documentation page and kind of go down to the bottom, okay, maybe not all the way at the bottom, here we are. These are all the types of data supported by NumPy. So here's my string, and there's additional documentation in here that tells you, say, how to specify what the length of the string is or how many bytes are used to describe a floating point number. Pretty cool stuff. We're not going to dive too far into those type descriptions. I started with a simple one where you can see that all I had to do to create my type string was call 1s, or actually I think s1 would have been more appropriate. Fortunately, NumPy is forgiving on this matter. Now that I have this data, I convert it from a map of types, which doesn't have any implied order, to a structured list of types. Now, if you've ever written in C, structured data types look a lot like a C struct. A structured data type holds on to both the names of the fields and each of their types. And instead of in a dictionary, it's in a list. Let me zoom in a little bit more. It's a list of tuples, which has a defined order. So here, and each of the tuples is the name of the field, the type of each member, and in this case, defining that I'm having a 2x2 array of single precision 4-byte floats in a field named Z. So what I do to create that structured data type is I pass in the list of strings, or the list of the items in my dictionary, which gives me this more truncated form. I've got a 8-byte integer, a 8-byte float, and a single character string of 1 byte. Now that I have this in NumPy, it's in a form that PyTables can work with it, and it converts it to its own format. Now, one thing I'll point out here, the format description for a PyTables has some additional information in it, such as what the default value for a row with missing data is. I'm not going to modify that here to keep things simple. All right, once I have this description, actually creating the place to store it within the file is very easy. I create the group, which again is the dictionary. I create the name of the key that's going to hold my data set. And then I pass it the description. What does that data set look like? How many rows and columns are there? I give it how many rows I expect to have. This doesn't actually matter for our purposes. You don't need to know how many rows are going to be available at the front, but this makes the storage of them more efficient if the HDF5 file has a clue about how much data it's going to see. Then I've passed some filters just to show them off. So filters, as we mentioned earlier, are things like compression. Here I'm saying compress this data with bzip2 at a moderate level, and you'll see later that I can read the data from this file without actually having to mark that compression is available. And I'll even show you why that is. Now I've created that table. To store data in it, I need to convert my Pandas data frame into a NumPy array that looks like this table. That's fairly straightforward. I create a NumPy array, an empty one, of the length that I want. It's a one, like the table, I need a one-dimensional array. And that table stores its own data type. So here you can see I've created a data type that looks exactly like what we provided before. I then fill this array with the data from my table. Here I'm using a trick from the NumPy structured data types. I'm calling a column name and writing the value for all rows using this syntax. I'll paste the documentation link to show you where I learned how to do that. So now I've got a NumPy array, and I save it to my table by calling append. So now my table object has the same data as my NumPy array did. Now, I mentioned earlier that HDF5 has caching, so it's very important to close the file first. As part of the file closing process, HDF5 might write data that it was previously only storing in memory while it waited for you to provide more data to be written. Closing flushes those buffers out, commits them to disk, and this creates a file complete with all the data in it. So here there's a lot of information that this printed out. In this notebook, I'll show you the key points, but I'll also talk you through them in the video. Here you can see that this file contains a description about where it came from, that it was written with PyTables version 2.1. Here is my dictionary that I created, the group, that holds my table. Now my table is a data set of currently 8 rows. It can be extended to as whatever size I want. It's a type table, which I didn't show you this earlier, but let's scroll back up briefly. A table is a special kind of way of describing data in HDF5. It is a sequence of records that all have the same name and type, or sorry, the same names of columns and types. That information, according to HDF5, must be decorated with the field names and those default values, which you may recall PyTables asked you for what they were, and it wrote them here. So my first field, default value, the fill value is 0, the name is A. Field 1, default value, field B. You get the picture. So that information is all stored here, and then I get information about how it is stored. This data is stored in blocks of 64 kilobytes, which, given the size of each row, is about 4,000 rows. On disk right now, there's only actually 136 bytes of information, but it took me 185 bytes to store it, even with using my compression. See here, the file itself tells me how to read it using this compression operation. Each of my rows, it even tells me what those data types are. It starts out with a long, which is a integer, a double, which is a floating point value of 8 bytes long, and at the end, a single byte that corresponds to a character. So 17 bytes in total. All of that is stored neatly inside. And because it's stored neatly in a way that's very predictable, Pandas can still read it back out as a data frame. But if you'll contrast this stripped down file information, well, it has a lot less cruft in there, which is great for my purposes. I wanted a file that I can send to my colleagues and have the page description detailing everything that's available inside that file be a lot easier to parse. I didn't need that extra information that Pandas puts in there, which I believe does magical things like allow you to run database queries very quickly. without having to read all of the file into memory at once, which is magical, but not something that I needed. For my particular subject, I needed just a very simple way of being able to cache all that information to disk. Oh, and if you look how you have it here, I stored about 118 kilobytes of battery data with only 6 kilobytes of space on disk. And if you look, here is the structure. I've got my names of the columns that I describe this information as, all neatly available, all well described in a way that others can go read this data into whatever program they're using to do their analysis of that battery health. So that locks it up for today. We'll quickly do a recall. What we showed you is how to work with an HDF5 file, which we've learned, and I'll show you the bit at the end, is a hierarchical structure like a Python dictionary that holds array data as its values very efficiently. You can use compression, you can use chunk sizes to allow reading to large data into memory, all unique features that make it very nice for storing large data sets like I work with in one of my projects. Instead of saving it directly through Pandas, which is a totally reasonable thing to do, what this tutorial showed you how to do is write them manually by first creating a group where that table is going to be, converting the data types from Pandas into formats that are documented in the HDF5 standard and therefore available in many other programming languages. And then finally, writing that data by first converting it from a Pandas data frame into a NumPy with those NumPy array with those exact data types, and then appending that to disk to give you this nicely ordered, very quick to read file. So that's all I have for today. I hope this was useful to you and that you're enjoying the holiday season. Take care.